Alright, today in this video I'm going to show you what a limit is in calculus. So let's consider the function f of x equals x squared over x. So now this function, if you graph it out, it looks something like this. Now upon first glance it does look something like that, but it actually has one more thing. It's got a hole right there. So this value here is undefined. And that's because this is at x equals 0, and when we plug 0 into this function, right, we get a 0 on the denominator. So that's actually not a possible value to find. But what if we do want to find that value? This is when we take the limit. So we write it as limit as x approaches 0. So it doesn't equal 0 because that's not possible, but it approaches 0. So we're going to get as close as we can to 0 to where it actually ends up being that value. So the limit as x approaches 0, and then we just write the function. And that equals some number. So now how do we find this limit? So the first thing we want to do is just use direct substitution, we call it. So we're just going to want to try and put that value into the function to see if it's even undefined. So here we know it's going to be undefined, so let's just start plugging it in anyways. So we have x approaches 0. So 0 squared over 0 is just 0 over 0. And this is one of our main indeterminate forms, they call it. Just something we can't determine. It's undefined. So we want to transform this into something that is defined. And there's two main ways we do that. The first one is factoring, and the other one is rationalizing. So let's start with factoring here. So we can factor this expression, right? So we always want to rewrite this limit down here. And then this x squared factors into x times x. This is over x. And then we can cancel one of these x's. So now we remove like the culprit that's causing this 0 over 0. Because this x would equal 0 and this x would equal 0. So therefore it's multiplying against all of the other things. Well, this is only one, but the other thing in the numerator causing the 0 over 0. So now when we have the limit as x approaches 0, it's just x. And then we can revert back to that direct substitution. So x approaches 0, this is equal to just 0. We plug in a 0 for the x. So now we know where that value would have gone if there was no discontinuity or hole or whatever they call it, right here. So this is the value that would have been. So basically what we're doing is we're finding a value that doesn't really exist, and we're kind of using a workaround to see what it approaches there. So next, let me show you what a limit not existing means. So that limit did exist. What we're going to do, what we want to look for is if it approaches from both sides. So take this function here. Let's say it has a hole there. And we want to find this, let's say this is just 3. We want to find, this is f of x. We want to find the limit as x approaches 3 of f of x. And we don't know what that is. So we need to find where it approaches on this side and this side. And it needs to approach on both sides. That's very important. So let's say we had something like this. Function maybe like this. So it's got that and then this. So it's like a piecewise function. And let's say this is also at 3. We wanted to find the limit as x approaches 3 here. Let's say g of x. But we don't know where to look for it. From this side it approaches here, but from this side it approaches here. So we really don't have a value that really works. So this limit does not exist. Whereas this limit, let's just say this is 2, this limit equals 2 because it approaches from both sides. And now you can also approach infinity, which would be something like this. So if you had the fractional function 1 over x, right? And that kind of looks something like this. So the smaller the number here, closer to 0 it is, the bigger the value of the function is. Because a large 1 divided by a number much smaller than it makes a bigger number. So if we take the limit as x approaches 0, we actually can't do this limit. Because this is going as far down as we can possibly go, so negative infinity. But on this side of 0, it's approaching infinity. And notice how this function, we have an asymptote here. it never touches 0, because 0 would make 1 over 0, which is undefined. So that's when a limit does and does not exist. Now, let's look at some examples of finding limits. So let's say we wanted to find the limit of this function. So now let's pull up our little checklist here. So we have direct substitution, factoring, and then rationalizing. So let's start with direct substitution. Let's say we wanted to take the limit as x approaches 3 of this function. So we start by substituting that 3. So 3 squared in the numerator minus 3 minus 6 over 3 minus 3. So we can see 3 squared is 9 minus 3 minus 6 equals 0 over 3 minus 3 is also equals 0. So we again have that 0 over 0 indeterminate form. So this means that we're going to have to factor or rationalize. So let's do that. So I see the top is a quadratic, and we know how to factor quadratics. This would factor in x minus 3, x minus 2, over x minus 3. And remember, this is still the limit as x approaches 3. So now we see this repeated factor x minus 3, which we can cross out. And if we pay attention here, this 3, when plugged into that factor, makes it a 0. So that's kind of the culprit of making it a 0 over 0. So now we just have the limit as x approaches 3 of x minus 2 over 1. And then we can revert back to that direct substitution, giving us 3 minus 2 over 1, which is just 1. So the limit as x approaches 3 of f of x here is just 1. Even though this value cannot exist, as it approaches 3. As it approaches 3, it gets very close to 3, but it never hits 3, and that would actually be 1. So now, let's try a rationalizing example. Let's take the limit as x approaches 4 of x square root of x plus 5 minus 3 over x minus 4. So now, let's review our terms. So we got direct substitution, factoring, and rationalizing. So we can try direct substitution here first, but you'll see quickly that we have, if I substitute 4 for all the x's, we have 4 plus 5 in the square root, which is 3. 4 plus 5 is 9, square root, minus 3, over 4 minus 4. So we get 0 over 0 in determinate form. So that means we're going to have to do one of the other techniques. So factoring, we can't really factor this expression, but we can rationalize it. And how we're going to rationalize is we're actually going to use the conjugate. So if you remember what conjugate is, it basically it takes advantage of this property here, a squared minus b squared factoring, which is factors to a plus b, a minus b. So if we want to remove that radical, we can square it. So right now we have what we look like an a minus b, so we need the a plus b. So let's just write this out here so we have a little more space. This x approaches 4 of x plus 5 minus 3 over x minus 4. And then we're going to multiply top and bottom by the conjugate of this one. So x plus 5 plus 3. The same thing on the bottom. So now we're just going to simplify that. So in the top, remember, this was following that a squared minus b squared pattern, so we can kind of redo that. So we still have the limit as x approaches 4. So now x plus 5 in the square root squared would just be x plus 5. And then this squared would be 3 squared is 9 minus 9 over, then we're not going to FOIL this out because you can see, right, this x plus 5 minus 9 is equal to x minus 4. Therefore, you can cancel it. And then that leaves us with just the x plus 5 plus 3 in the bottom. So let's rewrite this. So we have the limit as x approaches 4 of, now it's just 1 over x plus 5 plus 3. And now we can finally revert back to that direct substitution. When we substitute 4 in, we get 1 over square root of 4 plus 5, square root of 9 plus 3, which is 1 over, this is 3 plus 3, 6. So 1 over 6 is the limit. That's it for the basics of limits. If you'd like more, like a more advanced video, just let me know in the comments below. Thank you for watching. If you'd like to see other content like this, please check out my channel. Thank you.